Welcome back to BSpice. In this session, we'll focus on gas turbine basics. In fact, one of our viewers actually requested for this, and that's why I'm uploading. So let us go into the details of this basic session. So I'm going to explain this with the help of typical model, and later in this next video, we'll focus on one typical type of compressor, for example, axial compressor, wherein we'll run through the details and dive deep into the concept. So this is like a more of a prototype kind of video to understand the basics about the gas turbine. Okay, having said that, let us focus on the intro first. See, gas turbine is a heat engine, an engine that converts heat energy, okay, into a mechanical energy. So here the heat energy is usually produced by burning fuel with oxygen of the air, right? In that way, the engine actually converts the potential chemical energy of the fuel first to the heat energy, then converted into mechanical energy. So this is the basic concept. However, in a gas turbine as well as in other types of heat engine, only part of the released heat energy can be converted into the mechanical energy. Remaining all gone waste, right? So the remaining will be transferred to the atmosphere. Okay, this is about the basic intro. Few more to add on. In a gas turbine, 25 to 45% of the input energy is transferred into a mechanical energy. So the remaining 55 to 75 will be transferred to the atmosphere in the form of waste heat, basically exhaust losses. So the efficiency is around 25 to 45% only. So what is efficiency? Again, output energy divided by the input energy. Okay. So this is about the intro. Now I'll get into the operating cycle main part. What is happening inside the turbine? Okay. With the help of a open gas turbine cycle and a closed gas turbine cycle. Okay. In a gas turbine, the operating medium is air and gas, right? So the flow actually, the sequence flow runs through the various cycle. What is this? One is the compression here inside the compressor. Then second is the heating and combustion chamber. Okay. Then third is the expansion that is in the turbine. As simple as that. Okay. In an open gas turbine cycle, ambient air is sucked in, compressed in the compressor, heated in the combustion chamber by injection and burning of fuel, and then expanded through a turbine back to the atmosphere. So this is about the open gas turbine cycle. Operating medium of open gas turbine cycle is air, mixture of air and combustion gases. Okay. Now let us see the closed gas turbine cycle. Here, an enclosed gas, okay, runs through the same phase as in open cycle, meaning compression, right? Sorry, compressor, combustion chamber, and turbine. Same thing. So only difference is here. It is coming back here using this gas cooling, right? So the heating takes place in the heat exchanger and further expanded through the turbine must be cooled here. This is cooled before lead back to the compressor. So this is about the closed gas. So in practice, the open gas turbine cycle is completely dominating, and in this section we'll focus more on the open gas turbine cycle. Okay. So now this functionality, I'm going to explain with the help of a typical model. I'm not going to talk about the actual turbine and all. That will follow in the next slide wherein we'll talk about the axial compressor. Here, just to understand, I'll just explain with a bit of a model. Okay, tube model. So gas turbine consists of compressor, combustion chamber, and of course turbine, right? So how heat energy by the operating medium flow through these main parts, meaning compressor, combustion chamber, and turbine, is converted into a mechanical energy is explained by a simple model as shown here. Okay. So this is a tube equipped with a sample fan in both ends. Just visualize it. One of the fan is named as compressor. Okay. just for your discussion sake. Other is the turbine. Okay. So an external power source or a starter is connected through the coupling to the compressor, right? Okay. Now, to start with, the compressor is set into motion by using an external energy source such as a starter motor connected through a coupling, right? So in turn, the compressor creates an airflow through the tube, which then passes through the turbine, causes it to rotate, giving off a mechanical output, right? Okay, so the amount of energy supplied can be seen in the speed of the compressor, increasing airflow velocity and pressure together with the resultant turbine speed. Okay, so if the process goes on without any losses, practically it is impossible. But for the argument's sake, we say, okay, so it is without any loss. So the turbine energy output is equal to the energy sacrificed to drive the compressor. Okay, this is the theoretical. Okay, now, one more scenario. Once see here what happen. We talked about the function principle. Here we talk about airflow. The airflow is getting heated. Okay. The heating increases the air temperature. When we heat the air, it increases the temperature. Since the pressure inside the tube is created by the compressor, higher temperature of the air does not result in increased air pressure. So that is the point. I again repeat, friends, just watch. Since the air pressure inside the tube is created by the compressor, higher temperature of the air does not result in increased in pressure. Then what would happen? Yes, instead the air volume is expanding. Temperature is not increasing. Okay. I mean, the higher temperature will not increase the air pressure. Here, what is happening is instead the air volume is expanding and results in increased air velocity through the turbine. You got it? Yes. So, a large amount of energy is transferred to the turbine, giving a larger mechanical output. So, if the process goes on like this without losses, of course, it is not possible practically. So consider no losses. The turbine mechanical energy output is equal to the sum of the mechanical energy supplied to the compressor and the heat energy supplied to the airflow, isn't it? Okay. So now the heating airflow is we discussed. Now we'll talk about the self-sustaining speed. Okay. So increasing the heat supply, okay, meaning the turbine gives sufficient mechanical output to drive the compressor, right? Right. So if the compressor and turbine are in the same shaft, okay, mounted on the same shaft, the starter can be disconnected because the self-sustaining condition already reached, right? Isn't it? So at a self-sustaining condition, the mechanical output extracted from the turbine is just enough to drive the compressor. Okay, right. Now we have talked about self-sustaining. Now power generation. To get a useful mechanical output from the turbine, the heat supply must be further increased to speed up the engine above the self-sustaining speed, right? To make the gas turbine as efficient as possible by converting the heat energy into a mechanical energy, the design must be more complicated than we discussed here, right? We just discussed about in a simple model. But in practically, that is not the case. It is more complicated than we discussed in this model. Okay. So now we talk about this actual compressor. You see here, this is how, friends, the main features with cylindrical casing, containing compressor, combustion chamber, turbine, airflow, gas flow moving straight through the engine. So this is the basic look and feel of the, what do you call it, the turbine, right? See, this is your starter. This is your coupling connected here, connected to the compressor here, and this is your combustion chamber, okay, and this is your turbine, okay. So this is the simple funda about the working model of the gas turbine. In the next video, we'll talk about more on the type of compression. Okay, for example, we'll take a axial compressor as an example and we'll try to explain as requested by one of our viewers. Thanks for your support, friends. And once again, I request all of you to support whichever way you want. Okay, whether by subscribing or simple, just a thumbs up, or if possible, share with your friends. Okay, thank you. Take care. Bye bye. See you in the next video.